Okay, so let's we're talk about thermochemistry today. So you should have already read the chapter, but I'm going to kind of go over some of the highlights of some stuff that we need to pull out from that. Okay. So as you know, that thermochemistry is the study, thermo, heat, right, chemistry. So what we're going to look at is the study, the relationship between energy transfers. Maybe if my within chemical systems that deal with heat. Okay. So heat is one of the forms of energy. Okay. So we also have work. Is energy caused to move? Heat is the energy that's used to increase the temperature of a system. All right. So when we're doing that, first off, we need to talk about units. Okay, so this is important, and the book talked about it, but we're going to use joule is the unit for energy. Okay, so joule is represented with a capital J, and most of the time will be in kilojoules. Okay, because a joule is actually not that large of an amount, but we're using it in energy. So when we're talking about energy, when we're talking about joules, heat is also going to be measuring in joules, okay? And if we remember, heat is the energy needed or used to increase the temperature of a system. And let's talk about real quick what temperature measures, because that kind of helps explain how heat is actually, and temperature is actually related back to energy. So temperature is the average kinetic energy of the particles in the system. Okay, and so since temperature is a measurement of average kinetic energy, what we can do with heat is we're saying, well, as I increase the temperature, well, what's happening? The average kinetic energy is also increasing. If I decrease the temperature, then the average kinetic energy is decreasing. Okay, so that's how heat gets related back to energy. Okay, and this is a pretty important thing to remember here. Temperature is the average kinetic energy of the particles in the system. And we talked a little bit about that last year in gas salts and stuff like that. Okay, so all right. The two big things we want to look at when we're looking at thermodynamics, okay, there's two things. There's a system and a surroundings. And what we're looking at with thermochemistry, all right, is how the heat is transferred from the system to the surroundings and vice versa. Okay? So, sometimes the energy is transferred from the system to the surroundings, and sometimes it's transferred from the surroundings back into the system. And that's what we're going to be looking at, this interaction here. Okay, so most of the time the system is just the chemical reaction that we're dealing with, and the surroundings would be everything else. All right, so let's break that down real quick and go ahead and define some stuff with that. Well, first off, we know from the first law of thermodynamics that energy cannot be created or destroyed, but can be transferred. Okay? Or conserved. Okay, so energy is conserved. First law of thermodynamics, that energy is conserved So the energy that this system surroundings interaction has, whatever energy leaves the system goes to the surroundings, and whatever energy leaves the surroundings goes back into the system, okay? So energy is conserved and it's transferred between these two systems. So let's take a look at what that means. So let's say we have the system, and energy, and we're going to talk about an energy since we're in thermodynamics, we're talking about heat, right? As heat leaves the system and goes to the surroundings, this would be called an exothermic process. If energy enters the system from the surroundings, or heat enters the system from the surroundings, this would be an endothermic process. Or heat entering the system, endothermic. Heat exiting the system, exothermic. Okay? So what do we see here? Well, what we see is, in this one, an exothermic reaction, let's take an example of that. Like, let's say we have a combustion reaction, right? So let's say we have some methane here, and we burn it with some oxygen. Okay, so it's going to go to carbon dioxide plus some H2O. All right. So if this is my reaction here, well, we know some stuff about combustion reactions. What happens? If you're having a fire and you put your hands around it, what happens to the temperature around your hands? Well, it increases. So what's going on? Well, there's heat or energy stored in these chemical bonds here, okay? And when they're getting broken, it takes energy, but when these new chemical bonds are getting formed over here, they're releasing energy, okay? And that energy comes out in the form of heat. So it exits the reaction as heat. So this is an exothermic process. And what do we see with that is that the temperature increases, right? If I put a cup of water, okay, over a fire or over a reaction that, heats up, well, the temperature of the water is going to increase because I'm putting in heat to that surroundings from the system. Let's look at an endothermic process, like something that's going to take energy, okay? So an example is that if I had liquid water and I want it to go to gaseous water, this would require energy, right? You don't just see water boiling or vaporizing by itself. So what do I have to do? I have to put heat into the system to increase its energy to go to the gaseous form. All right? So endothermic and exothermic. So this would be endothermic. All right. So some other processes that are endothermic and exothermic. Anything that produces heat, any fire, any combustion reaction. Most processes that we see are actually, chemical reactions happen naturally or exothermic. And if the reason you think about this, really what we're comparing here is we're comparing, energy transfers or the internal states of energy of these chemical bonds, right? So if you think of it kind of like this, okay, so here's when a process is exothermic, right, it's releasing energy, or it's starting up here, here's where the bonds and the energy of the bonds start. And then as the reaction happens, well, the ball falls down the hill and then it ends down here. Okay, so in this case, this ball has more potential energy than this ball. Okay, so when it dropped down, well, its energy wasn't destroyed, it was transferred to kinetic energy, and there's some friction, stuff like that. Well, the same thing happens with reactions. When a reaction is exothermic, the reactants start at a higher potential energy than the products end at, and as they go down, the heat or the energy leaves the system as heat. Okay, so the opposite would be true for an endothermic reaction. Okay, you start down here, and then you end up here. Well, how do I get something from, lower to higher position? I have to add in heat. So you add heat. Okay. So in the case of these, if I was, balls and stuff like that on hills, well, it would just be gravity, potential energy due to gravity. What we have in chemical equations and chemical reactions here is the energy is stored in the bonds. And we're looking at the potential energy difference between the bonds here. And that's what gets that production of heat, or if I have to add in heat because the bonds go to a higher energy state. All right, so that's a real quick summary of the beginning of thermochemistry. So this really down here is really what we're going to start looking at. The difference in the energies between the bonds of the chemicals, okay, in the products versus reactants. So that's the big thing. That's really what we're looking at here. So when we talk about thermochemistry and heat transfers, this is really what we're looking at. Okay, are the energy, the bonds more stable, so at a lower potential energy in my products or in my reactants? And then how do I get the heat to flow from the system based on the breaking and making of those bonds? Right? So that's kind of a little recap of that, and we'll talk about that tomorrow over our Zoom session.